Okay, so before we talk about why Newton's method is such a great method, let's do a couple of examples that show how it works in practice. We won't do these for very long. So here's an example of Newton's method. It's a function that we've looked at before. So we know that the minimum of this function is somewhere around 2.5, a little bit to the left of 2.5 actually. And we'll start with an initial guess at x naught equals 1. So we'll seed our algorithm with x naught equals 1, and then hopefully it won't take us long to get to to get close to the minimizer of that function. So Newton's method is different to the direct search methods we've done before, in that it doesn't work unless I have the first and the second derivative. So this time, for this function, I've actually got to differentiate this twice. I actually have to do a tiny bit of work. So the one differentiates away. I've got to do the product rule on this. So I'm going to differentiate. I'm going to get an e to the negative x on 2, always appearing outside here. And then if I differentiate the first thing first, I'm going to get negative of negative a half. So that'll be a half times ln of x. And then I'm going to get, I have to differentiate this, hold this constant, and that's going to leave me with, if I get all of my minus signs correct, a 1 over x. Right, so 1 over x from differentiating the log x, a negative sign is that negative sign. A half from differentiating that with a negative cancelling out. And I've taken out the common factor of e to the negative x over 2. I also, the pain here is that I also need the second derivative. Right, so now I've got to do another differentiation. So let's see. I'll keep that out the front, and then I need to differentiate inside here. I'm going to get a half of that, keep this term the same, times and then hold this constant the same, so that gives me a 1, and then differentiate this, so this will be 1 over 2x, take away 1 over x squared, with a plus now. And that simplifies slightly. If I come up here, that's going to simplify to e to the negative x squared on 2. Negative a quarter log x. And then I can collect up these things. So actually, they'll just become 1 over x. So now I've got everything that I need. So once I have those, it's just a matter of plugging in, right? So I need to evaluate the first and second derivatives. Maybe I'll come over. Let's come over here. So f prime of 1, that's going to be 0, that's going to be 1, that's going to be e to the negative a half. So this will be e to the negative a half with a minus sign out the front. And the second derivative, so plugging 1 into this, that's 1, that's 0. That's e to the negative a half. That's going to give me 2 e to the negative a half. So I've got those, I can evaluate them. And now let's just do one step. Newton's method, which is going to be using this formula that's up here. So x naught is 1. Take away f naught, f prime of 1, which is that. So this is going to give me an e to the negative a half divided by 2, e to the negative a half, and they cancel out. And that's going to give me 3 on 2, which is nice. And then I could keep going. All right, so x2 is going to be 3 on 2, subtract f prime of 3 on 2, divided by f prime prime of 3 on 2, and so forth. So we could keep going. At that point, I won't. Let's just let the computer do it for us. All right. So if we look at the table at the right here, so we started off with a guess at x naught equals 1. Plug in x naught equals 1, you get 3 on 2, 1.5. You know, that number that I just didn't bother calculating is 1.95. And then pretty quickly, you start to converge on something. So after 7 steps here, you know, the difference between the 6th and the 7th step is, what is this, 1, 2, 3, 4, 5, 6, 7, 8, in the 9th decimal place. So this is converged to something very, very accurately, very, very quickly, actually, which is great. And here's what it's doing. So here is, you know, in the first iteration of this, really what I was doing is fitting a quadratic, right, a Taylor series, the first two terms of a Taylor series that's centered at the point x equals 1, right, to fit that quadratic. Right, so knowing the first and the second derivatives, you get that quadratic out. Then x1 fits another quadratic that's tangent to the curve at that point. x2, you can see that these points are getting closer and closer to the minimum, and my Taylor series approximation to the curve is getting more and more and more accurate. So Newton's method is exactly that. It's successively fitting Taylor series approximations again and again and again to increasingly accurate, you know, to centers that are increasingly close to the true minimum of the function. And that's how it works. So, you know, there's some, there are some points here. You know, we could keep going with this forever and ever. You have to decide on a stopping criterion. Unlike the direct search methods, you sort of have to make something up here. So maybe when the difference between iterations is sufficiently small, you stop there. You don't know beforehand exactly how many iterations you're going to have to do. That's a limitation. And there are also pathological things that can happen. So here's another example that I won't do on the board. Here's a function. You know, good for you to do this one at home to do the derivatives of that, and then take a look at it. I'll just show you what ends up happening here. So the blue curve is the function that I'm trying to minimize. Right, that has a minimum exactly at x equals 0, I think. And then the red curve is the tangent function. So that's the plot of f prime of x. Now the minimizer function, you know, applying Newton's method to find the minimum of the blue curve is exactly the same as trying to find the root of the red curve. Right? So using Newton's method with this tangent search method, the way that you've learnt this, the way that you would have learnt Newton's method before as a root finding method, you know, is what's sort of shown here. And so if you pick a bad starting spot on the red curve and fit a tangent to that curve, right, which is essentially what you're doing, trying to find this root here at 0. If you fit a tangent to the curve here, then you zoom over to a point that's over here between -1 and -2, and then you fit a tangent to that curve, and you look at where that intersects the x-axis, and you get back over to here, you end up exactly where you started from. So here, actually, Newton's method can break down. You end up in an oscillation. You never actually converge here. You just got unlucky. Right? You need to choose a new starting point. Yeah. That's one bad thing that can happen. The other, something even worse can happen, which is that you could actually just diverge. You can not converge to the minimum at all, even if your function is unimodal. So here's another way that this can break. You know, so the blue curve there is the function -e to the -x squared, and then the red curve is the tangent function, right, as the function showing the gradients of this. And if you choose a point that's over on the right here to start from, if you think about the root finding problem, so you fit a tangent to the red curve here, go to 0, you jump up to that point at 2, you cross the x-axis down here, and you actually start moving further and further and further away from the minimum. Right? So the sequence of points there is getting further and further away from the minimum. So your choice of x naught, the moral is that your choice of x naught here is important. And you might need to try a few different methods to find a good starting x naught such that Newton's method works. And there's not really any great guidance on how to do that, unfortunately. The plus is that when it works very, very quickly, which is what we'll talk about next.